In 3.4, we're learning about the different parent functions and also piecewise functions. Okay, so we're going to start off by graphing 3 different functions. I'm going to graph them all on the same coordinate plane. The first one is a quadratic function, f of x equals x squared. And you should be familiar with what this looks like. But if you don't know some of the exact points, you could always create an xy table. We know that this is centered at the origin, or has its vertex, I should say, at the origin, and it's symmetric over the y-axis. So I could choose x values of -2, -1, 0, 1, 2. Substituting them in, I have -2 squared gives me 4, -1 squared gives me 1, 0 squared is 0, 1 squared is 1, and 2 squared equals 4. So we could plot those points, -2, 4, -1, 1, 0, 0, 1, 1, 2, 4. And there's my parabola. Our second one, f of x equals x cubed minus 1, is a cubic function, and we'll have a cubic shape. If I want to choose some values, I could choose the same ones, -2, -1, 0, 1, 2. Substituting in, -2 cubed minus 1 equals -9. -1 cubed minus 1 is equal to -2. 0 cubed minus 1 equals -1. 1 cubed minus 1 equals 0. 2 cubed minus 1 equals 7. Plotting these points, -2, -9, -1, -2, 0, -1, 1, 0, 2, 7. And this is a curve, so a cubic function generally has this shape. And there's our graph. Our third one is the reciprocal function. So f of x equals 1 over x. Now, this has 2 asymptotes, one on the y-axis and the other on the x-axis. And I can use asymptotes to help me graph this. Often if you include asymptotes on a graph, you do it by using dotted lines. I'm going to create a table of values, ones that I'll use for here. Now I know that 0 is not going to be a value I'm going to use because there's an asymptote on the y-axis, but if I were to choose 0, I'd have to evaluate 1 over 0, which is undefined, hence the asymptote. But I'm choosing -2, -1, -1 half, 1 half, 1 and 2. So substituting in -2, I have 1 over -2. -1 yields 1 over -1, which is -1. Substituting in -1 half, I have 1 over -1 half, which is equal to -2. Substituting in +1 half, I have 1 over 1 half, which is 2. Substituting in 1, I get 1 over 1, which is 1. Substituting in 2, I get 1 over 2, or 1 half. Plotting these points, I have -2, -1 half, -1, -1, -1 half, -2, 1 half 2, 1, 1. Oops. I also have 2 1 half. And then when I draw them in, I have 2 branches, and they both approach the x-axis and the y-axis, but they would never actually ever touch them. So those are my graphs. Those are some common parent functions. X cubed minus 1 is a parent function that is shifted. We'll learn more about the transformations in the next chapter, next section. Okay, then I want to look at graphing a piecewise function. A piecewise function is a function that is defined in separate parts. Here we have it defined in 3 different parts. So, going to create a table of values. First, we're going to look at the first part of this function. And this is defined for x values that are less than 0. So I could choose -2, -1. And substituting in, I'll get -2 squared plus 1, which is 5. -1 squared plus 1, which is 2. And then I do want to substitute in my boundary value, but I'm going to put it in a different color because this point will not be included in our function. So for this definition part, if we put in 0, we would evaluate 0 squared plus 1 and get 1. I'm going to plot points, so -2, 5, -1, 2, and I'm going to put an open circle at 0, 1, so that part is not included. Let's look at the second definition part. So this is only defined for one value of x. X is 0. When x is 0, y is 2. So we will plot that point, 0, 2. Let's look at the third part of our definition, for x values greater than 0. So we will look at the boundary point at 0. I'm putting it in blue because we're not really including this point. But when x equals 0, y is 2 times 0 plus 1, or 1. Okay, then we'll look at x is 1, 2 times 1 plus 1, which is 3. We'll look at x is 2, 2 times 2 plus 1, which is 5. Let's plot. So 0, 1, we already have an open circle there. And then 1, 3, 1, 5. So the left-hand side was part of a quadratic definition. So we have our part of our parabola. We had our points, and then the parts for x greater than 0 is linear. So it's partially quadratic, partially linear, and then we have a point by itself. So for its domain, are there any values of x for which this function is not defined? It's going to keep going on the left-hand side forever. It's going to keep going on the right-hand side forever. Even that strange point where x equals 0, we do have a defined point at 0, 2. So our domain is all real numbers, -infinity to +infinity. Our range goes from 1, but that point is an open circle, so it's not really a point. It's not included in the graph, so that y value is not included. We'll have a curved parenthesis. And the graph keeps going up forever, so it goes to infinity. So the range is basically any y value greater than 1, but not including 1. Intercepts. So let's look at the x-intercept. Does it touch or cross the x-axis? No. So there are no x-intercepts. Y-intercepts. The y-intercept is 0, 2, where we actually have the solid defined point. Is it continuous? Well, if we're looking at this graph, could we draw this graph without lifting our pencil from the paper? No, because of that point at 0, 2, we'd have to lift our pencil from the paper. So this is not continuous.